Okay, our first example is number 6 in your exercises in 3.1, and the directions say find a power series solution of this given differential equation, then determine the radius of convergence, and then use the series in equations 5 through 12, so that's on page 195, to identify the series solution in terms of familiar elementary functions, right, or e to the x, sine x, cosine x. Okay, so let's go ahead and start. Okay, so our solution is going to be a power series solution. So let's assume it's a power series in x, representation in x. So I'm going to let y be equal to, so we have a summation of Cn x to the n, where n starts from 0 and it goes to infinity. So we have this infinite sum. And we can find the derivative because our differential equation is order 1, so we're definitely going to need it. So if we find the derivative, right, using the power rule, I'm going to bring my n, and I'm going to have Cn x to the, and then subtract the power. Now, since my power is n minus 1, I have to start at 1, right, because it doesn't make sense if I start at 0, because if n is 0, then I get x to the negative 1. And we have to start with a positive exponent in series. Okay, so let's substitute y and y prime back into our equation, right? So this is going to be our method of a power series, finding y prime, and now we're going to back substitute y and y prime right back in here. Okay, so if we go ahead and do that, we get x minus 2 times y prime. Well, here is my y prime. So that is, just going to write that in, n Cn x to the n minus 1 plus y prime, plus y. And of course our y is right here. So we have this infinite series that we started with. Okay, so there's our differential equation in terms of power series. So now we can simplify this a bit, right? We can distribute this x, right, into the sum, and then, of course, the negative 2 into the sum. So when we do that, we get, so we have n Cn x to the n minus 1 times x, right? This x that I'm multiplying, and my indices stays the same, minus 2, so minus, and I'll go ahead and write it inside, n equals 1 to infinity, 2 n Cn x to the n minus 1. So maybe let's write this in color here. So my x, I multiply it in here, and my negative 2 is right there, right? And then, of course, it's negative, so I just went ahead and wrote that outside. And then I'm just going to write my original one equals 0. Okay, so all I did was distribute, and notice, right? This is just some algebra. X to the n minus 1 times x is x to the n. And then this pretty much stays the same, right? There's nothing to do right now. And of course, copying this, Cn x to the n equals 0. So make sure you're neat with your power series, because you can easily make a mistake. And yeah, it'll be very hard to look back on your mistake. Okay, so we have, okay, so we multiplied in our x and our negative 2, and one of the things that you want to make sure is that your variable, okay, so we have these powers of x, so we have x to the n minus 1, and then we have x to the n. We want to have x to the same power, so x to the n, right? X to the, and then this probably should be some n, and then x to the n. So we have to change this guy in order to, compare our series. at the end. So we really want to change, we want to, well, change or shift the index. Let me make this, trying to make this small, but I write really big. Okay, so we're going to use a dummy variable. And remember, a dummy variable in math is, it's basically just a placeholder variable. So I'm going to let my dummy variable be k. You can let it be star f. It doesn't matter. I'm just going to choose k. Okay, so we're going to let k be equal to n minus 1. Well, if k is n minus 1, then what is n? Well, n is definitely going to be k plus 1, right, if we solve for n. Okay, so I want to rewrite this power series that I underline in terms of our k. Okay, so we have, I'm just copying everything else that I'm not using. So, okay, so we have the first summand that I didn't do anything with. Okay, so minus, okay, we have our sigma, and here n was equal to 1. Okay, so if n is equal to 1, well, again, we can replace, right, 1 for n, so 1 minus 1 is 0, so I know I'm going to start at k equals 0. So my index, I mean, it's going to change, and it's still going to infinity. So 2 times n, but what is n? Well, for my substitution, n is k plus 1, right? N is equal to k plus 1 times c sub n, and again, n is k plus 1, times x to the, let's see, well, we have n minus 1, but in this case, we call that k. Again, k is a dummy variable, which means it's just a placeholder variable. Let me rewrite that again. So k. Okay, so that's it for that part, and then I'm going to go ahead and rewrite my last summand, which I have not changed. Okay, so my powers are good, right? X to some power, x to some power, x to some power. And again, it's a dummy variable. You can call it anything you want. The next part is we want to make sure that we start at the same index for each summand. So in this case, we're starting at 0, 0, and then here this is 1. But I want you to notice, now this is not at every power series, but in this case, I'm allowed to, and I'll tell you why, but I'm going to rewrite this series as, okay, so whoops, everything else is the same, this guy, but I'm going to start at 0. Okay, so I'm claiming that this power series is equal to this power series. Well, to convince you, if just plug in n equals 0. Well, if n is 0, then, well, this is 0 times all this, which is 0. So the first term is 0 plus, and then you really start rewriting this again. So you're adding 0, and adding 0 doesn't change the value of anything, so that's why that's the same. And again, you can go ahead and expand it and test it out, and you'll see that they're the same series. Okay, so there's my n equals 0. Now remember, this is k is a dummy variable, so I can go back to n. So I'm going to change my k's to zeros. So n equals 0 to infinity, 2 times n plus 1, c times n plus 1 times x to the n plus, and then again, this last summand, haven't done anything with it, was our original assumption for y. Now again, if you want to convince yourself that this series really is the same as this series, just go ahead and start plugging the indices, right? If k is 0, well, the first term is 2 times 1, so that's 2c1, and then, okay, that's it. Well, if n is 0 here, that's 2c1, so you get the first term, you do it for the second term, and so forth. Okay, so now we can use power series operations, all right, just simplify these infinite sums. And if you want to look at the power series operations, you can look on page 196. And basically here, I mean, we have x to the n, x to the n, x to the n, right? And they all start at n equals 0, n equals 0, n equals 0. So I'm allowed to write, I'm starting at n equals 0, obviously it's an infinite sum, and I'm basically going to factor out that x to the n. So I'm left with n cn minus 2 times n plus 1 cn plus 1 plus cn, right? So all I did was factor out, right, this x to the n, x to the n, x to the n. Okay, so that's using power series operations, page 196, if you want to review that. And now we can use identity principle on page 199, because again, the goal is to determine what these coefficients are. So by the identity principle, right, this is on page 199, we can equate the coefficients. So this is going to imply n cn minus 2 times the quantity n plus 1, cn plus 1 plus cn is equal to 0. Okay, our goal is to get a recurrence relation in terms of the cn, again, because we want to find our coefficients. So here, let's go ahead and solve for, you want to solve for the highest subscript. So in this case, it's c sub n plus 1. But first, we can definitely combine some like terms. So we have n plus 1 c to the n terms. And then I'm going to bring this guy to the right-hand side. So that's going to be, just going to add that over. And we know n is not equal to negative 1, because we're working with power series, so we can definitely divide both sides by that, again, because n is not negative 1. And so we are left with cn equals 2cn plus 1, and then finally solving for cn plus 1, that's just going to be half of cn. Okay, so all this work was to get this relationship, which is called a recurrence relation, right? Specifically in terms of cn. So now, well, I'm actually going to do it in the next video because I'm getting to 13 minutes and I don't want it to take, it's already going to take long to upload. But in the next, continuing in the next video, we're going to explore this pattern, and we're going to see that we can successively compute, our C1, C2, and C3, and so forth in terms of the Cn. Okay, so I'm going to go ahead and stop here.